My name is Richard Garrison. I'm a manufacturing engineering student in the Industrial and Manufacturing Department at Cal Poly San Luis Obispo. My senior project is on developing a method to contaminate non-lead solder joints with gold.
Today, I'm going to talk a little bit about why this project is necessary and what it entails. I'm going to talk about the methods for attempting to solve this problem, the process I'm proposing, the results of that process, and the future of this project, as well as my conclusion.
Some of the benefits of adding gold to solder joints are that the gold layer is used to protect the nickel layer from oxidation and corrosion, enhance the soldering wettability, and improve wire bondability in some applications. Some of the negatives of adding gold are that when it contacts solder paste containing tin, gold tin-4 intermetallic compounds develop, which can be detrimental to reliability of that joint. The only current method to contaminate solder joints with gold is by gold plating. The point of this project is to design a cost-effective, robust method to contaminate a non-lead solder joint with gold. Once this process is developed, it will be eventually used to study the effects of gold at various weight percent concentrations within the solder joint. In order to begin solving this problem, experimental methods were used. This entailed developing multiple alternatives, choosing the best alternative, evaluating the theory, developing the actual process, testing and evaluating this process, and then determining whether this process was effective in solving the problem. After coming up with many ideas, 3 alternatives were developed that were then evaluated for their effectiveness. The first was adding nanogold to a flux mixture of zinc chloride. This led to the gold aggregating at the bottom of the solution. The second method was using nanogold, a dispersing agent, and a solvent with water. This mixture was not viscous enough and too difficult to apply. The third was using the previous method, but adding high viscous flux to thicken the mixture. In order to contaminate gold to the solder joints, the third strategy was chosen. Nanogold at 90 nanometers in diameter was submerged into the 3-mer captopropionic acid known as a ligand. This ligand casts a net around each gold molecule and aids in cross-linking with H2O molecules, making it then soluble in water. The THF solvent was used to aid in particle dispersion and reduce the amount of gold from settling at the bottom. Some of the pros of this method are that micropipettes are used to apply the gold paste. They are a very common instrument, cost-effective, and accurate to 0.1 microliters. Once the gold is in solution and fully dispersed, the particles are easier to control during application. There is also very minimal processing time to make this paste. Some of the cons of this method are that if the solder paste is not accurately measured, the amount of gold cannot be accurately applied at a certain weight percent. It is also a very manual process, meaning there are many opportunities for error to occur. So this is the process overview of the gold paste contamination method. First, we'll develop the gold paste, store it for future use, collect datum points on each surface pad on the circuit board, document those datum points, apply the solder paste, then take a laser scan of the solder bump in order to then determine the volume so that we know how much gold to apply. Then we will place the components, apply the gold paste, take it through the reflow oven, and then inspect the solder joints visually. Once the gold paste is made, we can then begin collecting datums with an OGP vision scope. By selecting 3 points on each surface pad, we can then calculate out the normal vector and centroid of each surface plane. This will then be used to calculate the volume of the solder paste applied to each pad. The center picture is the fixture used to ensure that the circuit board is taken in and placed back in the same position for each measurement. The third picture is just the OGB vision scope used to make all these measurements. After the datum points are collected, solder paste is then applied. A 5 mm thick stencil is aligned with fiducials and then taped in place. The SAC 305 is squeegeed over the surface of the stencil until all the holes have been filled. The stencil is then removed so that the solder bumps are now exposed. Once the solder paste is exposed, it can then be measured using the OGB vision scope again. A laser scan goes back and forth on the solder bump, collecting many points which will then be used to determine the volume. Once the volume is known, a certain weight gold percent can then be calculated and applied to the joint.
Developing the Excel program in order to determine the volume of solder paste was previously talked about in the last video. I just wanted to go over some of the basics to show you how I got the calculations that I did. Vector algebra was used in order to develop the program in Excel to determine the solder paste volume. The 3 points collected from the surface pads determine the board datum. The datum defined a normal vector and a centroid. The normal vector dotted with the point in space minus the centroid determined the perpendicular distance to that point taken on the surface. Once the perpendicular distances are known, they can be multiplied by the distance between points and the widths between scans to determine the volume of one point to another. The individual columns can then be summed up to estimate the volume of each joint. Figure 10 is a 3D representation of what the Excel sheet should try to capture. Once the solder paste is applied, it begins drying out. In order to speed up the process, a pick and place machine was used to place the components once the contour scans have been taken. This process is not only fast, but it is also very effective in the fact that the components are always placed in the same position. Once the components are placed by the pick and place machine, the gold can then be applied using a micropipette to transfer the gold from the vial onto the component leads. In order to dissolve the gold into the solder joint, the test board must travel through a reflow oven that heats the joints up and then eventually solidifies the joints, adhering the components to the test board.
The result of this project indicated that gold paste attempted to be applied at 1 weight% in this top board had minimal to no component movement. Gold paste that was attempted to be applied at 10 weight% was much less successful in terms of shorting the leads and component movement. The components had shifted over and gold had spread all over the board surface.
Some of my future plans of this process include doing a cross-sectional analysis using a scanning electron microscope to determine the actual gold content in terms of weight% of each solder joint. I like to optimize the gold paste to reduce the number of packages floating off their pads and to be able to apply the paste to leads closer than 50 mil. I like to do a complete reliability testing series utilizing this process to determine the weight gold % limitations within a non-lead solder joint. If this process was successful, I like to develop standard operating procedures so other people can use this process as well.
Once this project was finished, it was determined that the effectiveness of this process was inconclusive. The most important takeaways were that as the amount of gold paste applied to each joint increased, components were more likely to float off their surface pads. And packages with 50 mil lead spacings were cross-contaminated with gold paste from other pads. This project taught me a lot about an experimental process and how to solve a continuous set of problems. I learned a lot from this process and I hope you did as well. Thanks for watching.